Answer this. You make yourself a cup of coffee and you're about to pour the milk in, but the doorbell rings. In order to keep the coffee hot when you come back, do you pour the milk in first and then go answer the door?
Can I have my bowl back, please?
Or do you answer the door first and then pour the milk in? Which one would keep your coffee hotter for longer? To me, the answer seems obvious. You answer the door first, then come back and pour your milk so that your coffee stays hotter, right? Well, it turns out that that's actually wrong. In this video, we'll be diving into strange and often misunderstood scientific subjects to try and make sense of it all, and hopefully not go insane. To understand why it's actually better to pour the milk in before answering the door, you first need to know Newton's law of cooling, which states that the rate at which an object loses heat is proportional to the difference between the temperature of that object and its surroundings. To put it simply, hotter objects cool down quicker. So if you don't pour the milk in, the coffee starts off hotter, but then it cools down faster as you're answering the door. So when you pour the cold milk in, it lowers the temperature even further. However, if you pour the milk in first, then the coffee will initially lose a lot of heat, but then it will slow down and lose heat slower than if you didn't put any milk in. Then by the end, once you pour the milk in the other coffee will be slightly cooler than your coffee. Intuitively, this feels wrong because of something called the anchor bias, which is where people overemphasize the importance of the first piece of information. In this case, the first piece of information is the hot coffee, so your brain wants to preserve the initial heat of the coffee. And pouring cold milk directly on the hot coffee feels like the last thing you want to do. This is also the same reason that when you're negotiating a salary in a job interview, it's always a good idea to start high, then work your way down, because the initial high price serves as an anchor which makes you subconsciously appear more valuable than you actually are.
What kind of pay or salary are you looking for?
It would be really cool to get 6 figures, like dead serious.
At a canvas company? What are you, crazy?
Well, I'm not going to stop till I get 6 figures, sir.
That's what you're looking.
I want 6 figures.
Okay, well, there's the door right there. Good luck in trying to find that.
6 figures, please.
No.
Can I get that?
No, that's not.
I can't get that here?
No.
Okay, so we get all that, but what about when they say that electrons are both a particle and a wave? Or when they say that black holes might be a portal to another universe? It sounds like they're just making it up as they go along. When electrons are first explained to us in school, they tell us it's a particle, and we imagine in our minds something like a marble. It has a position, it can move, it can bounce off walls, bounce off other particles, but this is sort of a lie. An electron is nothing like a marble. But if you're teaching a class full of 12-year-olds, it's easier to just say particle and move on. Sir, what's an electron? An electron is both a particle and a wave. However, it doesn't have a definite location. Instead, we use a wave function which gives us the probability that the electron appears within a given region. So how do you find the wave function? So this is Schrodinger's equation, which shows us how the wave function of a quantum system evolves over time. Sir, are you having a stroke? Because what you've written there is just gibberish. I think we should call an ambulance. No, it's just maths. Look, this is the partial derivative with respect to time. This is the Hamilton operator. Yeah, he's just speaking gibberish. No one can understand what he's saying. To us, this makes no sense, and it feels like another lie scientists tell us because we're all too stupid to understand the truth. But this time, scientists are actually telling us the truth. On a microscopic scale, things can have both particle-like and wave-like properties, which doesn't happen in our daily life. On a large scale, particles and waves are two completely separate things, which is why it's hard to imagine small particles acting like waves. But in the 1920s, Clinton Davison and Lester Germer were firing a beam of electrons at a nickel crystal and observing how the electrons bounced off the metal surfaces. But they accidentally overheated the crystal, causing it to react to the surrounding oxygen. They tried to fix this by slowly heating it back up again, but once they resumed the experiment, the electrons weren't scattering randomly anymore. They were interfering with each other and causing distinct interference patterns, which is what happens when two waves intersect. This proved the suspicions of French scientist Louis de Broglie, also known as de Broglie, that small particles also have a wavelength, and that wavelength can be found using the de Broglie equation. Often when we learn science in school, we build images in our heads to try and memorize things as quickly as possible. Enzymes and substrates fit together like a lock and key. DNA is like the instructions for building an organism. Or my favourite, mitochondria is the powerhouse of the cell. Our brains naturally do this because it's easier to memorize simple analogies than it is to learn and remember the nuanced reality which often can't be explained easily to someone unless they already have a background in science. So in some cases, science teachers straight up lie to students or tell them things that might confuse them later when they realize that the analogy no longer holds true. Because a teacher's job isn't to teach kids the most accurate information or even set them up to be world-class scientists in future. Their job is to get them to pass their exams in this academic year. Click this video if you want to see more, and piss off!